today is kind of, I want to make sure that we're on the same page. So did you have any questions about chapters, the two chapters we did just now?
I kind of had one about kernels.
Okay.
So
you find them in Kentucky?
Yeah, corn popcorn.
Okay.
In the information I read about the kernel of a matrix also related it to the null space of a matrix.
Yes.
And then I saw one example like the one we did, only it didn't match my memory or how I would have notated it. Essentially, and I guess it's sort of the same thing, but instead of, I guess it's number 3 in chapter 9.
All right, well, let's look at this example first. Here's one example of a kernel, just to make sure it matches up. Okay, so for instance, here he says the solution set to a homogeneous equation. Right. All right. So here we have a matrix. Let's just make this big. M. So here you have a matrix M. So if you wanted to solve this, let's go through this. If you wanted to solve this, and you wanted a homogeneous linear equation, so how would you go about doing that?
First, I would row reduce the matrix.
All right. Well, let's go ahead and use our OneNote. It's not giving it to me. There we go. We'll get linear algebra up here. And it's not that one. Linear algebra. Right here. And let's make this big. And we'll go, I guess this is still chapter 10, so we'll add a page and we'll talk about kernel. Okay. All right, so let me copy that page. Okay, insert, screen clipping. Here's this. Okay, we'll make it bigger. Okay, so the homogeneous linear equation is M is going to be mx equals 0, right? And that's the 0 vector. All right. So you're saying, let's turn the usual crank. Whenever you have a system of linear equations, you have to create the augmented matrix, right? So what's the augmented matrix going to be here?
You're going to add 0, 0, 0 as the fourth.
Just
vector.
add this 0, 0, 0 on the end here. Okay. Now this one's actually quite easy to row reduce, and we can just do it in one step. Should I call on somebody? Let's see. How about you, Sheena? What's the row reduced of that?
Everything except the top row going away.
Yes, very good. Very good. That's exactly what happens. Right? You take this minus 2 times that goes away.
And then 3 minus 3
this one,
times
yeah,
that.
very good. So, and then what about the top row? Can you reduce that any farther? No, you can't.
Once you ditch everything else, it's
No,
just 0.
no, that's right, because it's got a leading 1, and it has one pivot column here, right? All right. So we're done with the row reduce. Oh, so now we want our, so this is our pivot, and then these two are free, right? So that means that the free variable is arbitrary, right? So so the free variables are arbitrary. So we can say, what's the best way to do this? Well, one way to do it is just write it as the three variables are going to be x1 plus x2 plus x3 equals 0. So you can write that as x1 equal to minus x2 minus x3. So what's your favorite way to solve this now? We want,
Take x1 to be positive 1.
so we say x1, x2, x3. Well, you want the general solution, right?
Oh.
All right. You want the general solution to this. All right, so let me ask somebody else. This is the minus sign. So, Christy, what would you make the general solution?
It's not just x1 equals negative x2 minus 6.
All right, let's go with that. So the x1 is negative x2 minus x3. But I need three components.
X2 and x3.
Just make it x2 and x3, okay. Now, that's one way to write it, but it's better to write it in another way.
Make two vectors.
Make two vectors. So because you have two constants, so it's good to make it into two vectors. It's going to be equal, so it's equal to, if I take out the x2, then what do I have here?
Minus 1, 0.
Right, and then if I take out the x3, then what remains is x3. Right. So this is the set of linear so in fact now we know that this is equal to the span. We can write this as a span, right? Span of what?
It's the span of the column space of whatever that matrix is.
Well, it's this. Well, but that's true. No, it's not. No, it's not. I can write this set as a span because x2 and x3 are arbitrary. So what's this the span of?
The null space.
What does span mean?
It means it covers all the options, right?
All right. Well, let's recall the definition of span.
Oh, you want to be technical?
Isn't that
definition?
arc 2?
Okay. Let's see. All right, that's not correct. Spanning sets. Spanning sets. Okay. So, for instance, here it says the vectors u. Here's an example of span. All right. Okay. So let's see what u is. U is this set of two vectors, right?
Yeah.
U is this set of two vectors. The span of u is
Isn't it
this
arc
here.
2? Isn't it the y is plane? No?
Well,
Maybe.
what this is giving you the general definition.
Oh, okay.
If I've got these two vectors, the span is the set of all linear combinations.
of those two vectors.
So geometrically, you think of that, one vector 20 here, one here. You take all combinations, it's going to give you the point.
Plane.
So that's what you should think about span. If I give you a bunch of vectors, the span is how whatever you can make from linear combinations. It is, notice the xy plane. It's the xy plane because the z is always 0.
Well, in that example, I was just
Yeah.
looking at arc.
All right, look at ours, okay?
My fault.
All right, look at ours. Let's look at ours. All right, now, but so can I write this as the span of a set of vectors? Just these two. It's the span of these two. So it's the span of -1 1, 0, and minus 1, 0, 1. So Sheena claims that this is the YZ plane, XZ plane, XY plane.
Well, yeah, to me it looks like YZ, but it doesn't include the origin.
It does include the origin, because I can do 0, 0.
Okay, okay, yes, okay, and this,
So in fact, it's neither nor,
neither nor.
because if it was the YZ plane,
Mm-hmm.
you couldn't have any non-zero x's. And here's the non-zero x. So it can't be the YZ
So it
plane.
can't be.
Can't be the XZ plane because there's a non-zero y.
Right.
Can't be the XY plane because
Because
it's
it's a
now you can have a skew plane, right? That's not parallel to them.
Okay.
Somewhere in between.
So it's
Okay.
just some
Okay.
some skew plane.
Okay.
It's not any parallel square direction. It's not something else.
Yeah, it's not.
Right.
It's skew is not
Right.
orthogonal. I got you.
Right.
Okay.
All right. So what we did was so here we say we have so that means the solution set to mx equals 0 is a subspace. We've seen that spans are subspaces.
Mm-hmm.
Okay, and this is called the null space of M, or the kernel. Okay, it's just a name. Now, kernel is like the nut, so in some sense, that's the solid part. But well, I don't want to go farther into that. All right, so let's find your example. You're looking for kernel. We'll find the example that. All right, I think it's this example, right? Aaron, this was the example you were thinking about. All right, this is in the same chapter. So here, do you see? Can you relate this to that example now? The u and the u prime, right? Here you're saying LU equals 0. It's a homogeneous equation. If this were a matrix, we'd just say L times U equals 0. That's the same situation we just had. We had M times X equals 0. So it really is the very same thing. Now what this is saying is that if I have two elements that are both in the kernel, and I take some linear combination of those two elements, then it turns out that L times that combination is always also 0. So that linear combination is also 0. Now we saw that here. That's exactly what we saw here. Same thing that we saw here. That if we have these two vectors, right? These two vectors are both solutions to the homogeneous equation. But so is any linear combination of those two vectors.
And so is this I just want to make sure I'm perceiving this right.
Right.
Each of those vectors is considered a kernel.
No,
No.
they're a
The kernel
vector in
is
the
not
kernel.
a
The kernel is a subspace.
Okay. So would the number of vectors, is the number of vectors in a kernel directly related to the number of free variables in the row-reduced matrix?
Well, you'd have to say the number of independent vectors.
Independent vectors, okay.
Yes, and the answer is yes.
So the number of kernels is,
Don't say number of kernels.
I mean,
Number
the
of
number of
vectors
And you
vectors,
can't say number of vectors. You really have to say the dimension.
the dimension.
Because there's infinitely gazillion many vectors here. I can take,
Right.
Yeah.
I can take 1 times this, 2 times this, 3 times this,
Okay.
4 times this. But the important thing is that these two are independent. Independent vectors give you the dimension. I'm sorry, but my dad is experiencing memory loss, so whenever I say dimension, I think dementia. So,
And
so that making sense?
yeah, where was,
So
what was
you're-
our
you're-
original matrix on this one again?
Original matrix?
Yeah, just,
So 1, 2, 3, 1, 2, 3,
Yeah.
1, 2, 3.
Yeah.
and so what we're saying is if we took that M,
Yes.
and we took these two X's that we just developed,
Yes.
either one of them, multiplied by that matrix gives us the zero vector.
You can try it.
Because, yeah, I can see it though,
Yeah.
because -1 + 1,
Yeah.
0 is
Yes.
0.
Yes, it's zero.
Okay,
Yeah.
okay, so,
So it all does tie together.
and then I guess one of my other questions was, that was a little iffy, it said documented as a span, and as long as we have a set, the set notate, it looked like set notation almost that you used.
Yeah, you can say span of that, yeah. I mean, there are two ways to write span.
I seem to remember us using the brackets.
Yeah, that's the other book, yes, yes,
Okay.
yes, that's particular to that other book.
Oh, okay.
But you can use that if you want. But here I wrote it one way. Right, you can write it this way.
Okay.
Or you can write it using the set brackets with a linear combination. That means the same thing. Means the
Oh,
same
so this would be okay then too, because I used set brackets with a linear combination.
Yes,
It's
that's,
easy.
yes,
That's-
that's, yes, it's the same, very simple,
Okay,
very simple, good.
that,
I
I
think you're good.
thought I had it. Now, this is more of a function of form. So like mine here is, this is what you get when you row reduce the matrix. I saw an example where what the guy did was,
Mhm.
instead of 1/3, 1/3, 1, he
Mhm.
did 1, 1, 3.
Right?
Is one form more proper than the other? I mean, they're saying sort of the same thing, but
Well, when you say row reduce the matrix, and 113 was a column in your,
it was not. You end up with 1/3, 1/3, 0 as the in the
well,
independent variable part.
yes, I see.
And
Well,
then-
I mean, you could change this, the row reduce doesn't matter. I could change this vector to -2 to 0.
Right,
And it
and
would be
then-
the same thing.
okay.
So I think that's what he's doing.
That's
He's
essentially
clearing
just
the
using whole
denominator.
numbers.
Yeah.
I
He's just clearing the denominator.
I
So
guess-
either way is fine.
All right.
That's perfectly fine. Okay. Any more questions on this stuff we just did? I guess there were other questions about kernel too. But this is the...
Yeah, that chapter didn't really give like much detail on what it was.
It's kind of like the same thing.
Well, yeah, I suppose not. I think that...
There's more examples in chapter 12.
Uh-huh.
So, our kernel is the null space, but so then our image
Image is the range.
is the range.
Yes.
Or we could say the span of the column space.
Okay, so let's look at that in this case. It is the spin of the column space.
Okay, I was mixing that up.
Yes, that's correct.
Okay.
The range is the spin of the column space, yes.
Okay. And there was another thing that we did in the last one,
Uh-huh. Well,
where it was like the span of the row space.
yeah, don't worry about that. Don't worry about that. That's called, I even forget what that's called.
That's what
Okay.
I was trying.
The two important ones are the range and the null space.
Range and null
Those are the two important ones. All right. Well, let me go ahead and move on to chapter 11 then. Let me do a new tab. Oh, here we go. Okay. So this is going to be chapter 11. So chapter 11 is bankruptcy, right?
There's also 13, 15, and
Oh, really? Okay. So this is about eigenvalues and eigenvectors.
Are we going to have web work for this chapter?
Yes.
Okay.
did you say blood work? I hope not. What kind of class is this?
Yeah, I will set up the web work. Okay. So let's think, now, the way he's, so I think I'm going to talk through the chapter because instead of making, this will be my video. So, but I want this to be more interactive so you understand. So he starts out with some examples. And let me give 2 examples that he doesn't give. Imagine you have a beach ball. Now, I'm sorry I didn't bring one.
I've got some in my classroom, I could have brought them.
Okay, yeah, I'm sorry. So well, this is exercise in imagination. You've got a beach ball here. Now, I can hold my 2 fingers like this and turn it. Well, like basketball players do, right? They put it on their finger and they turn it around. So it's rotating. Right? Now, if you got the basketball player doing this, there's always 2 points that don't move. Right? And the others turn around. Now, all right. Now, suppose I just take some basketball or beach ball and rotate it around. So I leave it in the same place, or a globe, okay? But globe, you know, globe always will go around. But suppose I have one. Well, some of those globes don't have it fixed, right? You can do it 2 ways, right? You can rotate this way, and you can rotate around. Okay. Now, it turns out that no matter how you rotate that globe, there's always 2 points that don't move.
I've got a wiffle ball if you want to use it.
Okay, yeah, okay. All right, that's fine. We can use. Okay, good. All right, so yeah, so what I'm saying is that, of course, you can do this. Right? But if I do, no matter how I twist it, let's say this is my starting position, right? Turns out that no matter how you twist it around, there's always a way, there's always 2 points that didn't move. Now, I can't tell where the 2 points are, but it's a fact. There's always 2 points that didn't move. And that's not easy to prove. But what that means is that there's always one way to, you can always choose 2 points and rotate it back to start, just keeping those 2 points fixed.
Okay, so the theory being that all those, these are force vectors in this case, right, that are acting on the globe spinning, they all average out to...
Well, not really force vectors. I mean, this is not a question of, it's just a question of motion, right? I mean, don't think about force, just think about direction. So, in fact, rotation is a linear transformation. There's something called a rotation matrix. And that rotation matrix will take all the points on the sphere and move them. Okay? Right? Each point is x, y, z, and it will move it to another x, y, z. And it's a rotation matrix. But it turns out that there's always x, y, z, and a negative. I mean, here you have x, y, z up here. You have negative x, y, z down here. There's always an x, y, z that doesn't move. Here you go.
Oh, you almost got it in my bag.
Okay. All right. So let's see. So I'll say 3D rotations. Okay. So you can say, so the points on a sphere are, I can write as x, y, z. And there's always a for any rotation, there is a rotation matrix. R, such that the new x prime, y prime, z prime, the new x, y, z is equal to r, x, y, z. Okay. So this is the new position, and this is the original position. Okay, and then it's a fact. So what I'm saying is that it's a fact that no matter what rotation, there always exists and I'll write it as x star y star z star, such that r times x star y star z star, well, I said x star y star z star doesn't change. It's the same play. So I can write that as r x star y star z star is equal to x star y star z star. Okay. Now you can write that rv equals v. Okay. So look at this form. You take the vector and you transform it, and it doesn't change the vector. Okay. So this is one example of a eigenvector. Eigen means, I don't know German. Eigen means, do you know German?
I was born there, but I don't know what it means.
Okay.
I can say my mother is lost.
Okay. I don't think it means that. Okay. All right, so that's one example. All right. Let me give you another example. See, the example he gives is quite complicated, and I'll talk about it, but I wanted to give some simpler examples first. All right, now, maybe you've talked about a population equations. Now, everybody, have you heard of Malthus?
Who?
Thomas Malthus? Okay. Well, anyway, you know that population tends to grow. And there are reasons for that we won't go into today. But, all right, but how does it grow?
Exponential.
So, all right, now why does it grow exponentially? That's exactly right. It's exponential growth. But why? Why does it grow exponentially? So the defining equation is the rate of growth is proportional to the population. Right? The more people, the more kids, right? Twice as many people are going to have twice as many kids. I mean, except for other factors, right? If all things being equal, right? If you have a constant birth rate, then you're going to have that. Then the rate of growth is proportional to the population. So I should say the rate of growth of the population okay, and I should say here this is assuming the birth rate is constant.
Now, when I think of proportional, I think of like y equals kx.
Yes.
But that's not y equals kx.
Yes, it is. Let's unpack this a little bit. The rate of growth of the population is proportional to the population.
Okay.
Right.
But it's
So,
exponential.
all right, yes,
It's
okay.
not
But what is the rate of growth? How do you express the rate of growth of the population?
I don't know.
It's a function of the population.
Now, what is rate of
Over time.
change?
Time is
What is rate of change?
Slope.
Slope. So what this is saying is that the slope is proportional to the
Okay.
population.
Okay.
The slope, not the, yeah, so that's the difference. You're not saying the population is proportional to time, you're saying the slope is proportional to the population. Now, slope, all you calculus people, what is slope?
Rise up and run.
Yeah.
Okay. All right.
High
That's
school
that's
math
that's
teachers
high
right
school,
now run.
not calculus.
So,
So,
All the high school math teachers.
Change in y over change in x.
okay, well, all right, yes, that's close. That's close. That's close. So the rate of growth,
Yeah.
Speed.
rate of
That's the
growth
nice one.
is equal to slope. Now, all right, so if I have a graph here, and the slope is here, right? The slope is like this.
So we're
What's
finding
the
the
derivative?
tangents.
It's a derivative, right? Slope is a derivative.
Yeah.
And he said it's change in y over change in x, right?
Yes.
That's what derivative is. Delta y over delta x.
Instantaneous.
Shrink them down.
Whoa.
Okay. Okay. So this is equal to the derivative. Okay, and this is a function, it's a function of t. So I have t here and I have population here. So if this curve here is p of t, this slope is equal to dp dt. Well, I should say, if I call this point, let's call this point t0, this would be dp dt at the point t0.
So we're pretty much finding the tangents of the line.
Well, the derivative is the, yeah, well, I'm only interested in the slope of the tangent. I'm not interested in the line, just the slope.
Right.
Because my equation said the slope is proportional to the population. Right, that's what I said. I'm not lying to you, that's what I said up here. Right?
Oh, I know what you meant.
Yeah. Right, the rate of growth is proportional to the population. Okay, so again, I'll write this out. So it's rate of growth is proportional to the population. And as I said, the rate of growth is dp dt. And here I'll put it at t0. Now, proportional means it's equal to some constant times the population. Okay? And this is true for all t0. So I can write this as, so I can just replace t0 with t. So I'm saying that dp dt is equal to kp, p of t. All right? And you probably have seen this before in one of your past incarnations. If you took differential equations, you saw this before. But but the solution of this is p of t equals e to the kt, or a to the kt. And you can check it, right? Because what is the derivative of a e to the kt? You remember? You guys got to start teaching AP classes.
Don't you have to have a certification for that?
All right, yeah, well, you need 18 hours. You need 18, so it's kind of...
It's, all right.
I'm not at 8 negative.
Well, it's quantity KT. Well, the derivative of a... So so I'll just put it in red here.
Trying to remember the derivative.
The derivative of e to the kt is equal to k e to the kt. You might recognize it if I just say, the derivative of e to the t is e to the t.
Right.
And then the k just comes from the chain rule. So I'll just
That's
put,
something I would have to look up.
all right, yeah.
Funny,
Okay. That's one of the things that really should be remembered, because it occurs so much.
That reminds me of Diffie cube.
It is diffie cube.
Yeah,
So-
that was scary, but-
Yeah. All right, so this is going to be equal to k times a e to the kt. So that works. All right, now look at the form here. What I have is the derivative applied to p is equal to k times p. All right, now see how similar that is to this one here. The one I had up here was rv equals v. Right? Now, the book has talked about how the derivative is a linear map or linear operator. So This is a linear map or a linear operator. Okay. So that means that P is an eigenvector for the derivative operator. Okay, so there's another example of eigenvector. And this was probably the first example of eigenvector. But since then, it's kind of exploded. You can find eigenvectors everywhere. All right, now let me go ahead and give his example. And I'll just do it separately. And you can read it, in your chapter. But this is kind of a cool review of calculus. So he says, suppose you have a string, a piano string or a violin string, and it's fixed here. So so this is the book example, and this is a string fixed at both ends. Okay. Now, let's see. Let me see if I need to get this right. Okay. Now, let's say, so let's say that this is x equals 0. And I'll say that this is x equals L. That's the length of the string. Okay. Now, what do you do with the violin string? You pluck it, right? When you pluck it, it moves. So each one of these points on the string will move as a function of time. So if I want to describe how the string is moving, I'm actually going to have a function of two variables. I'm going to have the x variable, which tells me where I am on the string, and then the t variable, which tells me what time it is. Same thing, I think we had something with sound waves also.
Yeah.
Sound waves, you have where the sound is and what time the sound is occurring. So I'm going to let, where'd you go? So I'm going to let f of x. Oh, let me see. I should say that this is I'm just going to pluck it in one dimension. So this, I'll call this the displacement. I mean, maybe I should, instead of string, just think of a telephone cord. That's what I'd like to do. You wiggle the telephone cord, right? And although you're wiggling it, that end is basically fixed. Right? So you wiggle the telephone cord, what does it look like? Don't you do that experiment in your?
Sine.
It looks like a snake, right? And if you do it the right, if you wiggle at the right frequency, you can make it be one big loop, or two smaller loops, or three, or four. It's kind of cool. If you haven't done it, it's a great experience.
Nobody has a telephone cord.
Not anymore.
I don't know if we could do it with this, but I'm not going to try. Okay. Okay. So I'm going to say let f. I'm going to say let f of x and t. All right. So here, let's call this point. I'll call this x0, and then here's the here. This would be f of x0 and t is equal to the displacement at time t. Okay, so let f of x of t be equal to displacement of point x at time t, because it's going to change. I mean, you know it's going to go up and down, kind of. Now, of course, the amazing thing is that you know that a piano string or violin string, I mean, it makes all kinds of weird shapes. And that's why you get overtones and things like that. So, so you can There's really a lot of variety into what kind of shapes you can get on a string. All right. So let's see. Okay. So are you with me here? So now we do the physics, and so from physics, and I won't tell you why, but this will just have to. From physics, f of xt satisfies the following equation. And it's the derivative of f with respect to x squared is equal to, now I have to think if it's plus or minus, and this is important. It's plus. Derivative of f of x and t with respect to t squared. And then there's also I need to think about this. I guess this is actually what you call 1 over c squared. And c is called the wave speed. And this equation is called the wave equation. And this is one of the great equations of physics. And it's also one of the great equations that has generated a lot of mathematics. You may know E equals mc squared. It's the same c. So c is the speed of light. But the reason why I call it c is because it's the speed of a wave. Light is a wave.
Isn't it unique because it has characteristics of both particles?
Well, that's not unique anything. That's the same thing is true of electrons, protons, anything. But originally, when they first started studying light, they discovered it was a wave. That's why you get colors and you get interference and you get all kinds of cool stuff because it's a wave, just like a water wave. And it's really quite incredible that you get the same thing with light that you do with water waves. I mean, you can get water waves can bend around corners just like light can. Water waves have interference patterns. I guess water waves don't have color, but that's just because our eyes are not tuned the right way. And same thing with sound waves. Same equation, very same equation. That's really quite amazing.
And why do they call it the light of speed, or the speed of light?
Well, I'm just saying C in general is called the wave speed. And the speed of light they use C for the speed of light because it is the speed of a wave. So I shouldn't say that this C is the speed of light in this case. I'm just saying C is called the wave speed. And for light, the wave speed is the speed of light.
It represents different things.
Yes, yes. I mean, it's got different, yeah. I mean, it can be the speed of sound, speed of light, speed of water, etc. Okay. All right. Now, something Aaron said is you can get sine waves. Okay. So my question is, how can you get sine waves out of this equation? How can you get sine waves out of this equation? The point is this: you get the sine wave. Basically, there's an envelope, and it varies back and forth between the envelope. So let me draw that picture. So let's see. So we know from experience. Well, let me make it blue again. We know from experience that you can get a solution that looks like this. It goes up like this, and then down like this, and it waves back and forth between these two. Right? So whoomp, whoomp, whoomp. Now you can also get one that goes like this. All right, so what's characteristic about this? Well, the shape doesn't change. It just goes up and down. So there's a constant shape, but that whole shape gets changed over time. So there's a constant shape, so there's a shape part and a time part. Okay? I'm not sure if I'm convincing you, but basically the shape doesn't change over time. So there's a shape part and a time part. Okay. We know from experience there are solutions like this. Okay, so the shape doesn't change over time. So that means that f of x and t gives me this displacement, and there's going to be a shape part, and then there's going to be a time part. And I can separate those out. Shape doesn't change. The whole shape changes the same way over time. Whole shape is multiplied the same over time. Okay. So I can write this. So the shape part is a function of x, and the time part is a function of time. Okay. So that means that f of x and t. Why is it doing this? Go away. Go away. So that means that so f of x and t. Let me just write this. It's going to be. I'll just call it f of x times g of t. I shouldn't write f because I already have f. Sorry. Let's call it g of x times h of t. All right, so now what I'm going to do is put this back into my original equation and see if I can figure out what's going on. Remember, my original equation was up here. My original equation was up here. Okay, so I'll put this back into my wave equation. The wave equation was d squared f dx squared equals 1 over c squared d squared f dt squared. So that means that d squared dx squared, and then that's times g of x h of t, just substituting, not doing anything fancy, equals 1 over c squared d squared dt squared g of x h of t. All right, now I need to address something. Is why did I use those scary looking curly d's instead of the straight d's? Have you seen partial derivatives before? So what this derivative means is that I'm only treating x as a variable and t is treated as a constant. And same thing here. ddt, the partial with respect to t means I treat x as a constant and t as a variable. So if I treat x as a variable and t as a constant, what can I do to this side here? Exactly. I can factor out the h of t. And then here I can factor out the t of x. So that's exactly what I can do. And that's going to lead us somewhere. Okay. So this is equal to h of t times d squared dx squared g of x. And that's equal to, I'm sorry, yes, and that's equal to, let's see, this is going to be g of x over c squared times d squared dt squared of h of t. All right, now comes the magic. I'm going to divide both sides by h of t times g of x. And this is a really cool trick. And whoever figured this out must have been very pleased. All right. So I'm just dividing both sides. All right, now what happens? What do I get on the left-hand side?
Your H's
H's are gone. So what I have on the left-hand side is d squared g dx squared divided by g. Let me write that. That really is kind of nasty. Let me do it this way. Okay, it's going to be I'll say d squared dx squared times g of x divided by g of x. And what about on the other side? I've got the 1 over c squared there. And then the g's go away. d squared dt squared. And this is h of t over h of t. All right, now, what is so amazing about this equation? This is a function of x. Only x. There's no t. This is a function of t. There's no x. What does that tell you?
That g of x is equal to
Not quite.
Not quite. Suppose g of x were equal to h of t. What would that tell you about g and h? G is a function of x. H is a function of t. How can that be?
Wouldn't that be considered inverse?
Well, if something varies as a function of x, but not of t, that means that g doesn't change when t changes. This whole side doesn't change when t changes. This whole side doesn't change when x changes. So I can change x over here. If I change x over here, this has to be true for every x and every t. What if I change x, no matter how x changes here, the t can't change? I mean, this side can't change. So the upshot is that neither side depends on x or t. Because if this changed when x changed, then this would have to change when x changes. But it doesn't. This only changes when t changes. And this side here too. This side changes when t changes, but this one doesn't. So neither side can depend on x or t. The way I can say that is that this side is independent of t. This side is independent of t. And this side is independent of x. So that means that both sides, because both sides are equal, that means that both sides must be independent of x and t. They can't depend on x or t. Okay, because if they change, they have to change together. But it's like this guy says, I only move this way. This guy says, I'll only move this way. So how are they going to move? They can't move. Because this guy tries to move this way, this guy says, I'm not going to move that way, I can only move this way. All right? So neither of them can budge. It's like Democrats and Republicans, right? So these are the, I don't know which is which, so you figure it out. But nobody's going to budge because they won't move in the same direction. If they won't move, they stay in the same place. If they stay in the same place, that means that it's a constant. Okay? So that means both sides are equal to a constant. Okay, and we'll call that constant lambda. We'll let lambda be the constant. So what I have is that lambda is equal to d squared g of x dx squared over g of x. And it's also equal to d squared h of t dt squared, and then this is over c squared times h of t. All right, now let me take this first equation here and rearrange it a little bit. How about I take this, so that means that, so let's look at this one first. Lambda equals, let me write it this way, 1 over g of x times d squared g of x dx squared. Okay. Now what I can do is I can multiply both sides by g of x. And then I get something that looks like this, which should be familiar now. Okay. Now, do you see why I went through this whole rigmarole now? What I have here, this lambda is a constant. Now this d squared dx squared is another linear operator. Linear map or linear operator. Okay. So I have this same form, linear operator times the function is a constant times the function. It's the same thing we saw with population. It's the same thing we saw with rotation. Same type of equation. So I can say this also has the form L times V is equal to some constant times V, where this is a linear operator. This is a vector. Functions can be vectors. This is a vector. And then this is a constant. So this is called the Eigenvector Equation. Or okay. Okay. This is called this thing is called the Eigenvector Equation. And this lambda is called the eigenvalue. And that takes us up to this place in the text. Okay. All right. Now here you see this here? Just what I wrote. Okay. So let me go to the next chapter. And here's the same equation again. Okay. So let's go down here. I think, all right, here we go. And then here you'll see this vibrating string example. I actually did more detail than him. But I think okay. All right, so now what he's saying, he wants to relate this now to geometry. Okay, so what we're going to do now is, we've talked about some very complicated vectors. We've talked about rotations and in 3 dimensions. And we've talked about derivatives. And that's kind of complicated, and second derivative. So now we're just going to talk about very, very simple vectors. The simplest vectors we really know are 2-dimensional vectors. So we're going to go back and try to understand this geometrically. What's going on? What is the geometry? What's going on? All right. Now, I have to be careful about this because he made a mistake. But some of this is right. All right, so here we have a linear transformation from R2 to R2. Now, what does linear transformation mean? It means you've got a vector, and the linear transformation will stretch that vector, move it around, something like that. Stretch it, rotate it, move it around. So you can think of what people often say is the plane is a rubber sheet. And linear transformation stretches that rubber sheet, but it leaves the 0 point in the same place. So you tack that rubber sheet to the floor, and then you stretch it in various ways. Right, so in this case, he's saying, okay, I'm going to stretch this rubber sheet so that these 2 vectors, this E1 stretches out to this one, and this E2 stretches out to this one. Now, notice that E1 and E2 are not eigenvectors. If they were eigenvectors, then L of E1 would be the same direction as E1. That's what an eigenvector does. Right? L of E1 has to be some constant times E1. So E1 is not an eigenvector. E2 is not an eigenvector. But this diagonal thing, you see this diagonal thing, if you stretch them, if you kind of do it symmetrically, this diagonal thing is going to go in the same direction. So that diagonal thing is an eigenvector. Right, this is kind of how he's showing it here. This is your original square. Here's the corner here. The corner stretches out to here. The corner's in the same direction. And this picture is wrong. All right, so that's kind of the geometrical idea of eigenvector. You do some stretching, and then there's one direction, well, just like the rotation. There's one direction that moves in the same direction. And you might think if you stretch one way, you switch the other way, and there might be 2 eigenvectors. And in fact, if there's one, there's always 2. Turns out that that's true. And we'll see why that is. Okay, so that's the geometrical idea. Now, one thing he didn't say, which I will say, because I think it's important, is that, so let me draw that picture again. Let's just do it here. So in R2, if I take let L go from R2 to R2. In this case, we have. Okay, so this is the E1 and E2, and then this would go to, say E1 goes to. Let's do a dotted one. Okay, so E1 would go to F1. This is L of E1 and L of E2. Okay. And then let's just say this is some vector in the middle. Let me just call this V. And then here you're going to say L of V is equal to some constant times V. Okay. Now this is when you do some stretching. But we also know that rotation is a linear transformation. So how about rotation? Okay. So for instance, if I want to rotate, if I have E1, E2 here, E1, E2. Suppose I rotate. Let's rotate by 45 degrees. Then what's the result going to be? What happens when I rotate E1 by 45 degrees? Where does it go? It's going to go this way, right? It's going to go up here. So I'll call this is L of E1. And what about E2? Where does E2 go? Still perpendicular, right? L of E2. Okay. Now, if you think about rotating, right? And let's say this is my origin. Right? If I rotate 45 degrees and everything goes like that, are there any eigenvectors? Are there any vectors that end up in the same direction?
Yes.
On that plane.
Yeah. Right. So
So on the same plane?
on the same plane. I mean, if I got a vector here,
Mhm.
it's going to rotate 45 degrees. Got a vector here, it's going to rotate 45 degrees. If I got a vector down here, it's going to rotate 45 degrees, not the same direction.
Mhm.
So in fact, it seems like there's no eigenvectors at all. In this case, there are no eigenvectors at all. Okay. So there are no vectors that end up in the same direction, because they all rotate. Right? So all vectors rotate by 45 degrees. So that means no eigenvectors. And then here I'm going to put in red, sort of. Okay. In fact, there are eigenvectors, but we're looking in the wrong place.
You add that another dimension.
Well, you have complex eigenvectors. But we may or may not get there. But as far as we're concerned, there's no eigenvectors. So you can see that there are cases where there's apparently no eigenvectors. So it's possible. In some cases, if you stretch it the right way, you'll get eigenvectors. Some ways, you stretch it the wrong way, it's no eigenvector. All right, so let's look at some specific example. And I think he gives a specific example here. Oh, Samuel, oh, okay. Okay. All right, well, anyway. So I'll just say feel free to call. Okay. All right. I should have gotten a notification. Let me see if my sound is... No, my sound is on. So not sure why I didn't get a notification. All right, so let me go back to the book and see what we have here. So let's go down. All right, so here. So now we're going to do an example. And I think I'll be lazy and I'll just follow along what he did, because he has it all written down. All right, so here we have a linear transformation, and the linear transformation on 1, 0 gives me minus 4 minus 4. So why don't I just draw it, because I mean, you're actually paying for this class, so I can't be that lazy. Oh, that's not what I want. I want this. Well, in case you don't know, loans have to get paid off at some point.
Oh, I'm already starting to pay them off.
Okay. Whoops, that's not what I wanted. Let's move it here. I think I have to do something else. Let me go here first. Okay, now it's good. Insert. I should give you a break in a minute. But, feel free to.
Oh,
Okay.
please.
All right, so we have this. All right, so let me just finish this, and then we'll take a break. All right, so here we have L of 1 equals minus 4 minus 10, and L of 0, 1 equals 3, 7. So what does that look like? Let's try to visualize what that looks like. That means that my 1, 0 vector this 1, 0 vector, I guess I'll make it red. And then if I take that according to my L, 1, 0 goes to minus 4 minus 10. So let me make the axis like this. Minus 4 minus 10 would be, well, minus 4 is back here, minus 10 is down here, so I got some red vector pointing down this way. Okay, so it looks like kind of a rotating, stretchy sort of thing. Its vector is longer and it's rotated. And then L01 is 3, 7. So let's make L01, I'll make it a different color, like orange. And then, so 0, 1 would be here. And L01 is 3, 7, so 3, 7 is 3 out here, 7 up here, so it's something like this. Whoops, sorry. So, but it's somewhere up there. Like this. It's not going to be the same line. It's actually not that different, but it's not going to be the same line. It's going to be something like this, I suppose. No, it's actually going to be steeper. It's going to be steeper, I think. Okay, so this is 3, 7. And then this is going to be minus 4 minus 10. Okay. All right, so can you imagine stretching this thing, stretching the plane so that the orange goes here and the red goes here? I think actually what you'd have to do is you'd have to flip it and then stretch it. Because here the orange is counterclockwise, and here it looks like it's clockwise. So to get from here to here, you have to flip it and then do some stretching. All right, now, so at this point, kind of the geometry runs out and the algebra kicks in. So let's see if we can find the eigenvalues, eigenvectors. Now, L is given by a matrix. So let's just call it, and it's going to have to be a 2 by 2 matrix. So let's just call it L11, L12, L21, L22. And if I multiply that by 1, 0, I get minus, what was it, minus 4 minus 10? Okay. So what does that tell me about L1, L2? What does that tell me about these coefficients?
It's L11 and L21.
That's right. If I multiply this matrix times this vector, it's just going to pick out the first column. So minus 4 minus 10 is L11, L2, so 4. Yes. So that tells me that L11, L21 is minus 4 minus 10. All right, now I have the 0, 1 also. Times 0, 1 is equal to, I guess it was 3, 7.
Mhm.
So that tells me what? Yeah. All right, so then in fact that gives me the whole matrix. So that means that L is equal to minus 4, minus 10, 3, 7. Okay? And I'll tune in next. So let's take a break. I think that's a good place we can pick up. We can take 15 minutes, it's okay. That was a long session. It's the longest I've lectured in a long time, at least in US. Oh, by the way, next week I'm going to be remote.
Okay.
So I'll be on Hangouts, and what I'll do is I'll call you all at 6. I think people are on at 6. So,
Same class time?
same class time, yes. Yes, Hangouts, yes. Let me pause my video. Uh-oh, my video, no, it's still running.